4, Part 2, Elastic Deformations. The first region we are going to enter is the linear region. And in this region, the Hooke's law will be applied. In the linear region, generally for metals, it will obey the Hooke's law, which shows a relationship between the stress and strain within the elastic deformation region, and which is a linear relation. For low stress, sigma, which is the low stress, is equal to E is the constant called the elastic modulus, times the normal strain value, which is the epsilon. For shear stress, we have tau times the tau is equal to G times gamma. G is the shear modulus, and gamma is the shear strain. And again, it is also linear. Slope of stress versus strain curve from uniaxial tensile test in linear region. Therefore, it can be defined as E. E is the normal. It is the elastic modulus for normal stress, and uniaxial tensile test, which applies a normal stress to its material, so it is E. Within elastic region, shape of the materials can be fully recovered by removing the external force or external stress. Example, estimate the Young's modulus of the material for the following stress strain curve. The first thing we need to identify the linear region. But again, we have already drawn it. And we try to calculate or observe the slope in the linear region. And by the readings shown here, we can calculate it. And E is equal to 850 megapascal. All regions of this elastic modulus, it is basically the boundings between metal atoms, are like strings, which can stretch and return to original length. But if you stretch it too much, it cannot fully return to the original length, which is represented by the end of our elastic region. First thing is, bond strength is directly proportional to the elastic modulus and the shear modulus, E and G. As it is because bond strength is directly proportional to shear required to increase per unit bond length, and as force is proportional to stress, and that means stress will be proportional to the E and G. And considering the structures, which I have already discussed in chapter 1, different materials have different structures. In general, ceramic will have a higher modulus than metal, and metal will have a higher modulus than polymer, due to their bond strength. Second, with increased temperature, you will have a lower value of elastic modulus and shear modulus. In terms of a microscopic world, when temperature increases, the kinetic energy will increase. And when the kinetic energy increases, the bond length will increase, which implies that the bond strength is diminished. As we know that bond is basically the electrostatic attraction between atoms and atoms, and which is proportional to 1/r squared. So this is basically our elastic recovery. Our demonstration. Let's say if the applied force is not too large enough, and the bondings will not be fully baked, and due to the attraction, it will recover again. Proportional limit. Proportional limit is the point where Hooke's law no longer applies, or the end of the linear region. Elastic limit is where the elastic region ends, and which is quite hard to determine. And we often use yield string value instead, which is determined by 2.2% offset method for metals. 2.2% offset method is an method to determine the yield strength, and yield strength is an approximate stress value that the material will start to yield, which is deformed, partially deformed after this stress level. We usually again reset using 2.2% offset yield strength value to approximate the yield strength of a material, as it is very difficult to find the yield strength without numerous experimental data. Steps for 2.2% offset yield strength method. First, you place your ruler on the origin of the stress and stress curve. Again, you adjust your ruler to follow the straight line of the curve in the elastic region. Again, you offset 0.002 units and draw a new straight line. The intersection between the straight line and the 0.022 offset line is the 0.2% yield strength value. Take the yield strength from the following stress strain graph. It is an example. The linear part, which is marked by the red line shown here. Then we offset the ruler. Here it is a 0.002, which is equal to 0.2%. And the red line is parallel to the blue region, the blue linear region. The answer is the intersection, which is 215 megapascal, based on the method we discussed about.